Okay, let's start again. Okay, this part was a little bit technical to get this lemma correct, and the lemma is saying you, if you search for the best rank k approximation, what you should do is you should go with the top k singular values, and that's what's written here, right? No matter what k is. From that you already get that the order of these is very important, right? So this is only true if they are ordered by, so we said that the singular values, the s's, they are sorted by decreasing magnitude. So now you should go with the highest ones. That's what it's saying. And that's why it's called principal component analysis. That's what the principle means, right? That you should go with the highest ones first. So if you go, this is a very nice kind of greedy algorithm. That's very rare that we have that. This is saying you get the optimal thing for k if you just greedily go with the first k. That's a very rare situation where we basically never have in reality, but here we have it. We can go with the first k. So and now we also understood that the UK stuff, so which is compression, are followed by reconstruction. That's clear. Now what this equation here means is that it actually explains what this has to do with the SVD. So if you just write UK times x, it's not so clear. But the thing on the right has quite a clear interpretation. So the thing on the right is this very small diagonal matrix. So just a small square k by k is non-zero, actually diagonal. And then it's multiplied with the full U and V matrices. So what the expression on the right is called is the truncated singular vector decomposition. So let's make some space. So this is the truncated SVD. And that's a very important concept. And what does truncated mean? That's exactly the fact that you forget everything else. You just go with the first k. So truncated SVD of the first k components. Okay, why is this equation true? That's actually also not so hard. So to see the first bit, we just plug in the definition of the SVD. So the SVD is exact. So here I have my x. I can replace x by the full SVD. That's what's happened here, USV. So nothing changed other than that. And now the interesting part is the second equation. Why should this thing be the truncated SVD? And that's also kind of easy to see. Maybe you see it. Because the thing in the middle, you see that U is multiplied with itself. So UK is multiplied with U. And that's the thing we can actually exploit. So that's what you have here. UK times U. So that one, it's not hard to see that that's actually, yeah, what is it? What do you guys think? Anybody? So it's, well, it's an identity matrix. I maybe heard it from you. So that's what it is. It's the identity matrix k by k, and then you have put some more zeros at the end. So what's the end? So this is actually a k by d matrix. So yeah, because it has k row, and it has d columns. Why is it? Because remember, U is a square matrix. It's d by d. So, and why is this the identity? Because this is an orthogonal matrix, actually orthonormal. Because what we're doing here is we're taking the first sum of the columns of k of U. So we're taking each of these k columns, pick one of them, multiply with all the columns of U. And we said, well, all the columns of U are orthogonal anyway, so that's why you get the identity matrix here. And well, yeah, you just have much more columns on the right, so everything else is 0. So that's very easy to see that this matrix, which is in light blue, that's basically the identity matrix of the right size. Okay, so once this is a identity matrix, padded with some zeros on the right, so now what we have is that this diagonal matrix is multiplied with the yellow stuff, the S, which is also diagonal matrix. So what does it do? It's just, well, yeah, keeping all the S entries which are from 1 to k, the first k ones, and the other one it's setting them to 0, so canceling them out. Maybe let's write the S matrix in red, but I hope this is clear that this actually proves the second equation here, which you wanted to prove, that this is equal to the truncated SVD. Okay, now maybe that's now more intuitive, so because now we understand the connection to SVD, so it is SVD, but after k you stop. Okay. Any question about this? Too fast, too slow? Yeah. Why does UK change to U? You mean from here to here? Or?
No, the equation of UK times UK transpose, so the first UK is on the left.
Oh yeah, this one, yes. Okay, you're right. So this, I said this is identity. Okay, so you're right. So UK has become U. So what you mean is from here to here, right? Yeah, does anybody see that? So, yeah.
Perhaps we don't care which one we're using because we multiply by S and multiply by
Yeah, you're kind of saying it doesn't matter which one we use because they get multiplied by a diagonal matrix. You said the S, that's correct, but actually it's even the blue diagonal matrix, even that one is canceling everything to 0 except the first k. But you have the right intuition, yeah. What was your approach?
Yeah, if you have UK times UK transpose, then you do the identity, right? The identity with the zeros. And then just one S instead of an N, you can keep U.
You're saying this is the identity?
With some zeros columns.
So that's actually not necessarily the identity, this one here. That's not the case, because for that to be the identity we need to keep all the columns. So, but you're right that this one here is the identity. So yeah, this is a good point. We have to be a bit careful that it's not U with itself is always the identity. So you can only do it if you go back here. So I went back a bit too far. Oh, I'm sorry, Clément. Maybe.
I need to start another one.
Sorry.
Yeah,
Okay, so U with itself is the identity. That's kind of correct, but this only works if you talk about subsets of entire rows here, or entire rows here. So it's not okay to just take the first part, multiply with the. It's not okay to ignore columns here to then still get the identity, because what the blue thing is saying that only if I take a whole row of U with another one, then it's the identity. So that's so be careful when you multiply these things together. So everything on this slide is true, but now if you start only talking about the first k columns, then we have to be a bit careful. But if you talk about the entire columns, those are orthogonal. But parts of rows are not orthogonal necessarily. That's why that's why here we have to be a bit extra careful when we do this decomposition. So because if you look at this part here, UK times UK, then you would ask part of a row is orthogonal to part of another row. That's not the case. But if you talk about columns, so that's the middle part here, UK times U, that's okay. There we talk about the entire columns of U or UK, doesn't matter. So the entire things, they are orthogonal. That's why this blue matrix here is the identity followed by a lot of zeros. So that's this matrix. So here the 1 is a matrix, so it's kind of this diagonal matrix. Maybe I write it better like this. So that's how this looks like. That's okay. And now this also should answer your question. So why can we forget about this K here? It's because when you take UK together with this matrix, then that's actually the same as taking U times this matrix. Because the diagonal thing, you will just select the first K columns. So that's why it doesn't matter if you write UK here or U times this matrix. So it's indeed okay to drop the K here, because your SK matrix only cares about it takes care of selecting the first K. So yes, I hope that was not too confusing, but so yeah, why do we care so much about this equation? It's because of things like that. It's really helpful for you to think what these things mean and to get the dimensions right and see what is orthogonal to each other. So now we see that the truncated SVD can allow us to do PCA. So okay. Any other comments on this, or something was unclear? Maybe if you have a minute, then do this step by step to be really sure and extra safe. I was maybe doing 2 steps at once. Then, so now we have this tool. Now we can do the compression by using the first K singular vectors. And now what is this useful for? Let's make this more concrete. So let's look at the real data set, and let's see if we can compress images, for example. So here is a set of images. So what we have here is, again, as always, the data points are the columns of our X matrix, and on what you see on the top left, so you have all these images here. I don't know how many. There are 28 images. So X is this matrix which has 28 columns. And what's D here? So for one image here, I have D features. The features here, they are the pixels. So I have, every image has D pixels, and here D is 250 or so, because these images are, let's say, 50 by 50 pixels. Okay, so one image is one column in my X matrix. And I have 28 images or so. Okay, so then what we do is, now let's just do PCA. We say 250 features is too much for me. Can I compress this? Can I use PCA with k equal 10? So just the first 10 components, so that's quite a drastic compression. I go from 250 to 10. So this is the compression. And then what you see in these images here is not the compressed versions, but it's actually already the reconstructed images. So what has happened here is again the reconstructed matrix, which is again in the image space, the pixel space. So remember, reconstruct after compress. So if you remember, this first one is the compression, and then the second one is the reconstruction. You can use a linear map to go back to the image space. Okay, so what has happened here is that actually we have found 10 vectors, so k equal 10, which are kind of, they're not really a basis of our images, but almost. So they are, what are these UK vectors, right? So we have found 10 of them, the 10 most important components or directions. That's our UK. So what they are is, they are actually images, and they kind of form a basis in our space. So they allow us to express images. Because if you look at this expression here, then so the part on the right, the part in purple, if you just look at one image, so that's one column of X, then what this does is this is a vector. So it's actually a K vector. So given an image, so this is the case if you only look at one column of X. So I take one image, I compress it. So what does that mean? So that means I've gone from 250, that was my green vector, that's the guy here, right? I have taken this vector, I compressed it by applying UK transpose. Now I'm down to 10 dimensions. So now I have these 10 numbers which describe my image. And what then happens is I will just take these 10 numbers. So that's my K vector. And then multiply it with these columns or UK. So that means I found a weighted combination of these 10 basis images which give me the reconstruction. And yeah, because K here is very drastic, so you would ask if this is still good reconstruction, but if you look at it, it's surprisingly okay, right? It's quite nice that you're going from such a drastic number of pixels down to 10 and still get well, it's recognizable. So okay, and the funny thing is, so that yeah, first of all, this works. The reconstruction error is not so bad. So I mean, there are different ways to measure the reconstruction error. Here we always talked about Frobenius norm. Actually, the lemma I showed you also shows you can also know that the same thing is the best approximation also in the operator norm, which is another matrix norm. But you can ask, maybe there's another norm which I want to measure my reconstruction error, then it's not so clear anymore, but for the easiest matrix norms, the singular vector decomposition gives you the best reconstruction. And it works in practice. So the singular vectors here, they're actually called eigenfaces. So if you want to play a bit more about with this kind of thing, then you can look this up and you can see that it's an interesting meaning, right? Because they are orthogonal to each other. They are kind of spanning the space of faces. That's the UK vectors I'm talking about. They're describing the main direction in this space of faces, right? Which have the highest, which explain this data set of faces the best. If you just need to decide on K orthogonal directions, then that's what they are. So we are not showing the eigenfaces here, but well, you can look at them if you compute your UK for your choice of K. Okay, so that's a nice way to do compression, and it works. And any questions you have on this? So I'll comment a bit in the end on how you can actually compute this UK efficiently given the data X, because for large data sets it's quite important that this is actually fast. So even reading your input X can sometimes take a long time when D is very large. So can you compute this UK quite efficiently? And the answer is, yeah, it's quite efficient. It's not so easy to distribute it on many machines, but on one machine this works quite nicely. This is you only need the most basic linear algebra operation, which is give me the first singular vector. And this can be used to get you all the K. Any questions on this space? This is a bit the approximation view, finding the best approximation to your data set. And if there are no more questions, then I will move on to the interpretation of this, that we can explain a bit what this means, to explain the data best in terms of having the lowest variance. So, okay. So this is in the image space. So you can, that's why you could not look at the purple thing alone. That would only be in 10 dimensions. So in the image space here, we look at already the reconstructed one. On the next slide, actually, I can show you the same data set when you look at the purple expression here for a data point. And so now you get a data point in the K dimensions. So you went from D to K for every data point. If you look at that point, so then you can do it for K equal 2. And again, see if you get a meaningful approximation or meaningful representation of your points. And you actually do. So this is actually quite surprising. This is really the same data set. And what you see here is that these are photos of the same color, means the same person. So they are photo of the same person. So this is, we were able to reduce our dimensionality from 250 down to 2 and still give it kind of a meaningful representation. So the two features we now got, they are quite meaningful. I mean, here maybe the approximation is quite bad, but we don't care about this here. So here we care about the new features we got in the reduced dimensionality. Are they any meaningful? So let me clarify the coordinates here. There are two coordinates. I don't know, you can call them y1, y2. What are these coordinates? That's exactly here the expression, the compression actually. So here we have saying k equal 2, which is taking two vectors. We projected our data down to these just two dimensions. Maybe that would give you a bit of bad reconstruction if you just take two, but it gives you very interesting features. So if you don't know anything about the data set, this is actually maybe the more useful application of PCA. I mean, there may be better compression techniques than this, but for interpretation, it's very, very useful. So we always have high dimensional data. We cannot interpret it, cannot visualize it. But here, by doing PCA with 2 dimensions, I can at least look at my data. So remember, the colors are maybe not there, but now by looking at the projected data set, which is in 2 dimensions, so now you maybe see there's an interesting pattern in my data. The same people have ended up close together, so are they actually, this is the same individual, which I think here is the same row of the visualization. Yeah, to be honest, this is not the hardest data set in the world. Maybe they are very controlled, but it's actually quite a big data set. You can download it. I think it's called a Yale Faces data set. If you want to play around with this, then you can do this, and also in the labs, you can try out how this works. So there are much more images than the one I showed here. So there are actually thousands, I think. Yeah. Okay. So that's a nice property of SVD. Very important that one thing is compression, the other thing is interpretation by reducing the dimensionality. So to finish this, we have two more things to discuss, and one thing is to make clear that this is very related to matrix factorization, that you maybe already saw when we discussed the math, when we discussed this equality. So you always saw that they're products of matrices, right? And that's the intuition that, oh yeah, this is just another kind of matrix factorization. That's what we're going to do here. And after that, we're going to give the probabilistic interpretation that we will also see that this captures the highest variance of your data. And that's the plan for the remaining 20 minutes now, but I think we will only do the matrix factorization part. This is very easy. So why is PCA related to matrix factorization? Again, so basically what I said is here is your SVD. So yeah, it's a matrix product. That's why. So remember, we always had this approximation of X as a product of summing W times Z. Or maybe some of the entries of X are approximated, or maybe all of them are approximated. And here we see that all of them are approximated, and it's actually perfect. So it's equal. It's an equality. We were able to write X as equality as a matrix product of two matrices. You can make, well, the different choices you can do. You can say my U is my V matrix, or you could also group it the other way. You could say this is my V matrix, and the V is my Z matrix. So take your three matrices, group them into two. Now you were able to write your X matrix exactly as a matrix factorization. And again, it's nice, the property that this is perfect. There's no error happening here. So it becomes a bit more interesting if we ask the same thing about the truncated SVD. And that you can imagine that, so now if I don't go to the full K, but only the first few entries of K, do I still get a good approximation? We discussed this a bit in this lemma, and that's what we're going to briefly look at now, and it's very clear that this is going to give you a good rank K approximation. So that's basically what this lemma tells you. So let's look at this briefly. Sorry for the wall of text, but so what we want to look at here is that, so if you do the truncated SVD, same, you remember the definition. You decide on a K, and you only go up to that number of eigenvectors or singular vectors. This is saying that you get the best rank K approximation to X, which is written here. And why is this? This is again, it's shown in the lemma, which is like the main theorem about the singular value decomposition. So yeah, you can really ignore the text here, don't worry. So this is really the same thing. So SK is the same definition as we had. So SK is again this matrix, which is just K by K here, and 0 everywhere else. And the truncated SVD. So this gives you a matrix which is a rank K matrix. That's also quite clear because S only has K non-zero elements, therefore only K non-zero columns. So if you multiply it with V, you will have a rank K matrix. If you multiply with VU, you still have a rank K matrix. So that's a rank K matrix, and the lemma before showed you that this is the best rank K approximation you can do here. And in the equation I showed you, we saw that the thing in the middle here we're talking about is actually the same as the truncated SVD. So the truncated SVD is the best rank K approximation. I think I'm maybe repeating myself then. So that's what we showed here. Right. Okay, so that's again why this is a good idea. And let's just see, now we talk about matrix factorization, and it's just a little bit of notation, but nothing mathematically happens to, if you want to convince yourself that also the truncated SVD is a matrix factorization. So of course it is. It's a product of 3, and it's even easier because I have set the middle part to 0, except just K entries. So if you do the same thing here, you say my first K columns, like that's my V, and then the other one, that's my Z. Then what you have is actually, now you have a matrix factorization which is of this form, so which has only K columns, and that's the additionally nice thing which you didn't necessarily have before. So okay, so recall again, before we had a matrix factorization which was U is a square matrix, so this is a D by D and then D by N. So that's not so nice, right? But now if you do the truncated SVD, then what we have is actually, we have only K columns in W and the same in Z transpose. So now we're back to matrix factorization with few columns, and that's exactly what we did when we did K means, and also when we did mixture models and matrix factorizations for the recommender system. So all I'm saying here is, if you look at the truncated SVD, so here is it. And again, this is maybe your question again, why shouldn't this be a U in the first place? And yes, it will be the exact same thing. It actually should be a U, but so it's going to be exactly the same thing because the SK matrix kills all the columns which come after the case 1. So this is the truncated SVD, and I write it as W times Z. What I have done is I have written my matrix as a product of this form of just few columns, and that's very nice because now I actually get a compact matrix factorization. The thing before, like working with square matrices, remember that's basically impossible. We can never do that. But here you can choose your K very small, so you can choose like 10 as we did, or even 2. And what this tells you is that, PCA of the K first components, that's giving you a matrix factorization of just K columns, of K latent factors. Very easy, it's basically just renaming what we already had the truncated SVD. Now we're just saying our UK we call it W, and then the other part we call that Z. So that's what's happening here. So yeah, and this is actually also very efficient to compute. You can choose your K, and same discussion comes up again. How should I choose it? So if you want stuff to be interpretable, then that's easy. Then maybe you're going to go with 2 because we can only visualize 2 dimensions. If there's other restrictions you have, maybe you can deal with 10 features, then you go with 10. Or you could choose it to have a good reconstruction error, if you care about that. Or you could use it, you could also tune it as a hyperparameter to see if it benefits your application. Maybe you do some more stuff after this dimensionality reduction later, then you could see what dimensionality would have been best for my application. So often, yeah, if you do a smaller K, then later on you will be more efficient, but you might lose accuracy. So this is the exact same discussion as we had in K-means, where we also needed to choose the K. So here you can choose your K to do dimensionality reduction. This is a nice collection. This again, so why do I care so much that this is related to matrix factorizations? It's because this shows you that, yeah, matrix factorizations, they actually do dimensionality reduction for you. That's what it means to multiply two matrices which have this small k as their inner dimension. And that's what you see here, and we can also interpret it clearly because we said that the columns of U are have a nice interpretation as faces, or the main directions in this faces space, and then the other part of the deal, the Z matrix, which is S times V, that also has a clear interpretation. That's the projection from your original D space down to the K space. So the V matrix here, or the Z matrix, that's your compressed data set. So okay, maybe that's a good point to stop. And then next Thursday we will talk about decorrelation, that this has the interpretation to minimize the variance in your data. So okay, see you on Thursday.